All right. So my name is Clayton Coleman. I'm an architect for OpenShift. I've been a Kubernetes community contributor since near the very beginning. And today I'm going to talk about stateful sets. If you guys, sorry about that. If you guys came to this, you probably saw a different title on the schedule. And I talked about stateful sets. I think it's really important that we get this out of the way up front. This talk is absolutely 100% not about pets. This is about stateful apps. Just recently, we changed the name of pet sets to stateful sets, and there was a big discussion in the community. And the idea here is that the general idea of a pet is it's something you care about, and so we're just going to be a little bit more precise, and we're going to talk about state. But during this talk, I'm absolutely guaranteed that I'm going to say pet sets. So if I say pet sets or stateful sets, I mean the same thing. So what does a stateful set mean? Why do we create stateful sets? What's the point of this talk even? Kubernetes is a programmable platform for building applications. Everything in Kubernetes is about a pattern that makes applications easier to run, administer, and keep running. And so keeping running is really important. If you have an application that's down, it's not much of an application. The real world, unfortunately, is not so nice to us. Kubernetes is supposed to be flexible and able to recover from failures. There's really two solutions to dealing with failure. There's two solutions for dealing with failure. These are pretty common patterns. The first one is detect that something bad actually happened and restart the application, move it someplace else. This is often called mean time to recovery. If you plan for this, you can actually be pretty effective. The other option is running multiple copies, which kind of depends on the first one. I'll talk a little bit more about that in a minute. So recovery, Kubernetes is actually pretty good at recovery. This is one of the fundamental principles of how Kubernetes is built. The idea of Kubernetes is you say, this is what I want to run, and the infrastructure tries to keep it running. So if you only need 3 nines of availability, 99.9% availability, that's 8 hours of downtime a year, more or less, unless I did the math wrong. And for a lot of simple applications, that's a lot of downtime, right? I mean, 8 hours, if it takes you 3 or 4 minutes to restart and you have less than 10 or 15 outages a year, you're well within that budget. So Kubernetes is really good at two things: restarting things that crash, as well as detecting nodes that have gone down or that have problems. And in this case, in Kubernetes, if you detect that something's wrong, there's a process that'll come along and it'll say, you know what, this pod's not working anymore, I want to stop it, and another one will get started somewhere else on the cluster. But that's just for simple applications. If you start building more complex applications that have more dependencies, you might depend from your front end on a web service that also depends on a database. And if you start adding more and more web services because you're building a microservice infrastructure, what actually happens is that the margin for error tends to be a lot smaller. It's not just if your application fails, it's if any of the dependencies fail and you can't recover from that. So detecting and recovering can work, but the bigger and more complex your applications get, the less margin you have for transient failures. So the naive solution is we replicate. If you've got a stateless web application, and that's a keyword, stateless, replication is really easy. Just spin up 15 of them. One of them goes down, you don't care. But unfortunately, replication is actually a really, really, really hard problem the moment you're dealing with something that actually matters that has to be consistent. So Kubernetes is really good at replication. In Kubernetes, there's the first primitive above a pod, which is something that runs containers, was a replica set. And in this case, you say, I want one of these. And it goes in, runs in the cluster. So imagine that Harrison Ford is running on your cluster somewhere. And then you say, you know what? I want to have some backup. So now I have 3 Harrison Fords. But because a replica set is about creating copies, there's a wrinkle. If you're storing data on each of those 3 copies, you can get into trouble. So the easiest way you can get into trouble would be, you tell everybody to go store some data. And the first Harrison Ford says, yep, I got it. And suddenly, if you go back and ask all the Harrison Fords what the value of A equals 1 is, you're probably not going to get a very good answer. And this should be no surprise to anybody in this room, but I think it's building up to why we think the replication isn't enough. So as part of the design process for Kubernetes, we started with pods. We built on top of them replica sets. Replica sets says just create 3 copies. And we know that we want to help people deal with state. State is a fundamental part of the applications we run. It's not just about web services, it's about databases. It's about message queues. It's about applications that write data to disk and then send that to other places. And so as part of the research for this, we kind of geeked out on data. There's been a long discussion. This is not a new topic in the community. There's an immense amount of research out there. There's an immense amount of types of systems that actually store state. And this is just a portion of this spreadsheet, but early on we went through and kind of tried to catalog a lot of the patterns that we've seen. On the far left, you might have NoSQL and SQL databases. The trade-offs here usually are kind of the ones that we're all kind of familiar with. So if you've heard of the CAP theorem, you get to make a choice when you have distributed systems. You can focus on consistency, or you can focus on availability in the event that something is partitioned. And so we tried to go through this thing and say, what are the common ideas that come out of all of these types of software? And again, these are just components that people tend to reuse. There's an almost infinite number of applications that actually have state that exist in the real world that aren't represented here. So a classic example might be if you have a large JEE application that's been ticking over for 10 years quite happily now, and you have a session store. That might be using Java serialization to do in-memory copy across those machines. That's a stateful set. The session data has to be replicated across the cluster. There's data, and if one of those machines goes down and your state's gone, a user who has a shopping cart or a web order or something like that comes back in and suddenly their cart's gone. These are older problems, but they still carry through today. So we looked at all this data, and I think it's important that I stop here and say, if you're running stateful things on Kubernetes today, they do work. It's possible today to set up a replication controller or a replica set and use a persistent volume. And if you set things up right, your data is going to be preserved. If a failure happens, it's going to tick over. But our goal is not just to make it possible, but to make it easy. If you have a workload, if Kubernetes is the goal, if the Kubernetes goal is running applications, and some applications have state, it's kind of silly to say, you know what, you can run state, but there's all these rough edges, so we're not going to help you. So the stateful set is taking some of the lessons, is going through the patterns that we see, and boiling them down to a couple of core concepts. So a stateful set is a little bit like a replica set. It replicates software, but it adds 2 things, the idea of identity and of tracking state. And state's a real catch-all term. For the sake of argument here, it really means access to storage or access to something that is persistent beyond an individual instance. So pods, as you may be aware, are built on top of containers, which are ephemeral. So in Kubernetes, if you schedule a pod and that machine gets wiped off the face of the planet, if your data only exists on that machine, data's not coming back. Kubernetes makes it easy to attach persistent volumes to your machines that might be network attached. You might be using a cloud provider with AWS or GCE, and you've got persistent disks where the cloud provider has done all the hard work of letting you pretend that data doesn't matter and these machines are all fungible. But you might also be running on bare metal using NFS, iSCSI, Fiber Channel, Gluster, Ceph, any of the other plugins that people have been adding. And that state, whether it's on persistent volumes or not, we want to make it easy to reason about. So because state is important, because state means data, safety first. As a user of Kubernetes, if you use the system and it doesn't help you understand what it's doing and what the failure modes are and how you can hurt yourself, it's not a very good system. Right? If you trust your data to the system, but you can't understand and expect it to work the way you want, designed for the administrator or the application author or the human, it's not a very good system. So we kind of formalized the 3 laws of stateful sets. May be familiar to some of you. A stateful set may not injure your state or through an action allow state to come to harm. Formalization of that first principle, which is do not lose data that you trust to the set. And yeah, sure, this is programming, things are hard, people always make mistakes. But first and foremost, we shouldn't lose data or by not helping or telling the user, allow that data to be lost. Second, take orders, do what you're told unless it conflicts with the first order. So we want to fail safe. So if you say do something stupid, we want to make sure there's enough patterns and things built into stateful sets that say, that was stupid, I'm not going to allow you to do it. Or if you do it, here's why this is going to cause you a problem, and I'm really sorry, but I'm about to lose your data. And finally, a stateful set must maintain its members as long as such protection does not conflict with the first or second laws. This would be the general idea of there's the trade-off that I mentioned before, consistency versus availability, is kind of a fundamental principle of distributed systems design. Can't work around it. So a replica set in Kubernetes leans towards availability. A stateful set is going to lean towards consistency. And because it makes that trade-off, when we have to, we will prefer to do nothing and take the hit to availability than to violate what you told us to do or to lose your data. And so again, these are just guidelines. There's not actually written into code. We don't have a positronic brain or anything behind this, although I wish we did. So I'm going to start with a really quick demo and then come back and talk through what's going on in the demo. So I'm going to show you not having access to wireless. What's the wireless password? Oh. Wouldn't be a demo without it. All right. What was it? Cloud native? OK. So I'm going to show you guys OpenShift. I work on OpenShift. OpenShift is a distribution of Kubernetes. We had a bunch of other stuff around Kubernetes in a kind of opinionated way, but ultimately, under the covers, it's still raw Kubernetes. So I'm running OpenShift 1.4, which is built on top of Kubernetes 1.4. It's pretty easy. We try to keep the numbers the same, except when we ship it to people, and then we add 3 for some arbitrary reason. So in OpenShift, an OpenShift project is just a Kubernetes namespace. So what I'm going to do is I'm going to take a ZooKeeper example written by Prashanth, who could not be here today because he made me do it. Prashanth put together this as we were doing the alpha work for PetSet. So what I'm doing is I've got a list of Kubernetes resources, and I'm just adding them in and creating them here. I'll show you a little bit more of the details, but I'm creating a service and a PetSet. Remember, we're going to rename PetSets, so just follow me along on this. And then I'm going to create some storage. Now, the wonderful joy of JSON. I should have tested this before. OK, I'm going to do the easy way. Never trust a UI. OK, so I'm going to create ZooKeeper here. And this would have worked if I'd properly formatted my YAML. And my clocks are all screwed up because VMs are awesome. So I've created a PetSet here. I've created a service. The PetSet's going to go scale up to pods. A bunch of stuff's going to happen in the background. We're going to see. I talked a little bit about the idea that we're going to be predictable and help you not mess up. So one of the things that people tend to get wrong is they start a whole bunch of stuff at once, and they all try to do things. And it's not necessarily easy to reason about the order those things happen in. So the way that a PetSet works is we start the first one up, and then we walk through the set. So that's a simplification so that you don't have to reason about what happens if all 3 start up at once and fight. I've got the logs here of showing the pod. It's going to come up. You're going to see the second one come up. And then hopefully by the time I come back to this, they'll all be created. So you kind of saw a little bit of this in the UI. So what is a stateful set or PetSet? A stateful set is designed to stamp out identical copies of a pod. And this is a pod template. So if you've ever created a replica set or a daemon set in Kubernetes, this should be really familiar. It's just, I want to go create an OpenJDK container, and I want to mount in a data directory. We're going to create multiple copies. So I say I want 3 of them. And the name of this set is Zoo, just because it's faster or easier to type than ZooKeeper. The special thing about pet sets and stateful sets is we talked about identity. The identity is the idea that even as individual pods come and go, there is an instance of the software running that thinks it's the first one, and there's an instance that thinks it's the second one, and there's an instance that thinks it's a third one. If one of those fails, we're going to use the name, and this is just the name of the pod. We're going to use this as the thing that we organize on. So there's never going to be, getting ahead of myself here, we're going to replace zoo2 or zoo1 or zoo0 with another instance that thinks it's zoo1. We want, and the state part of this is the second part, which is if you have a replica set today, it's an identical copy. So you'll say, create 3 copies of this pod template. Each one of those is going to point to the exact same volume. Now in Kubernetes, if you're using a block storage device, which says I can only be mounted to one system at a time, what's going to happen is only one is going to actually start. The other 2 aren't going to run. And that's because ultimately at the end of the day, what Amazon and Google and Azure and Ceph provide is there's a lock on that storage in the back end, and it's saying only one machine at a time can access this volume. But if you want to have 3 members that each have their own volume, you'd have to go create 3 replication controllers, 3 replica sets, and then go fiddle around with a bunch of details, which means you can't scale them up. So in Kubernetes, the PetSet adds the idea of a volume claim template. So today in Kubernetes, when you want storage, you say, hey, I want to go get 1 gig of storage. And what'll happen is at creation time, instead of just creating this one once, for each new member we create, we'll create a uniquely named one. So I'll have zoo0, which is my first pod, and it'll actually point to datadir0, which is the persistent volume claim created for it. So each pet or each stateful set member has its own volume. This really depends if you've used persistent storage. This actually really heavily benefits from having dynamic provisioning. So that's a feature that was introduced in 1.3 in an alpha form, is in 1.4 in a slightly better form. Storage classes were added in 1.4 as alpha and are starting to come out. So the idea of dynamic provisioning is you just say you want storage, and if you happen to have a pretty awesome storage provider, they just go off and they create a volume for you on demand. It makes it a little bit fiddly to demo on your laptop, and that's something over time we'll address, but we're starting to get there. And then it has to be possible to discover those other ones. So if I have zoo0, zoo1, and zoo2, almost all clustered software needs to figure out how to talk to those other members of the set. And so in Kubernetes, I said the word discover. In Kubernetes, the answer to service discovery is services. So we've added some features to services, which I'll talk about in a few minutes, that make it easy for the individual members to go find each other, but also for someone who's talking to this application to either say, you know what, I don't care about which ZooKeeper instance I'm talking to, I just want to talk to ZooKeeper, or to go find the individual members of this set by name. And then, it's really important, safety first, we'll never allow 2 pods with the same name to run at the same time. I'll come back to that in a minute, but the idea here is that if 2 people think they're the same, you could have pod 0 or zoo0 running at one point in the cluster. If you could get another one that thinks it's 0, and the 2 of them are talking to different members of the set, you have the dreaded split brain. Right? Both of those guys are participating. You don't have 3 members. You have 4 members. You don't have a quorum or a majority. Instead, you have a split. So I'll come back to that in a few minutes. The way the DNS schema works is we've added a couple of new alpha and features that are moving into beta that I specified a service, and this is just a normal Kubernetes service that I created. And I added the stateful set controller when it creates those pods adds a little bit of info that tells the DNS service how to identify that particular member of the set. And so if you saw, it says zoo0, zoo1, and zoo2, those correspond to the names of the pods. And it's just the simplest possible system that could actually work. If you ask for zk.mins.service.cluster.local inside your Kubernetes.cluster, it's going to return 3 A records, the IPs of each member of the set. There's some tricks around DNS. I'm sure some of you are aware DNS can be a fiddly beast at the best of times. If you ask for the ZooKeeper set, what you're guaranteed to get is you're never going to get 4 members here, But you could get the possibility that if one of these gets replaced and comes back, you might get another one in between. Another feature that we use is that we added in Kubernetes is the idea of an init container. So when we started Kubernetes, you have containers in a pod. You can run 1, 2, 3, an infinite number, not actually an infinite number of containers at the same time. Those all start up at the same time and move forward. They can share volumes. They can talk to each other over the local network. But it was really important for us to be able to separate out the responsibility for setup from actually running your container. So if you have a container that runs ZooKeeper, there might actually be things that you need to do ahead of time. You want to generate a config file. You want to go find out who the other members are and write that config file out. In the example that I'll show, Prashanth actually got really clever, and he said, you know what, I don't even really want to maintain a Docker image that has ZooKeeper in it. I'm just going to use the JDK, and I'm going to download from a particular URL the version of ZooKeeper, and I'm going to put it on disk, and then all the other containers in the pod are going to use that. So there's a number of ways that you can use init containers. It's not coupled to stateful sets, but it is a tool that can be used to separate out the logic in your pods. If your application needs to wait for another service to come up, like if your Java enterprise application doesn't really like it if the database is down when it starts up and it gives a big nasty error, you can write a bash loop in the command arguments here that says, can I ping the database? Can I ping the database? Can I ping the database? And just wait until it comes up. Sure.
So each of the instances seem to be getting an IP address from the service cluster anyway?
Yeah, so the question is they're each getting an IP address? Yes, so these are the pod IP addresses. Yeah, and we'll talk about that at the very end. There's an infinite number of features that complex clustered systems need to work. And one of the focuses has been getting the core ideas in place. These are pod IPs. Pod IPs are fungible because pods can come and go. It depends on your network. Down the road, there's been a request for the ability to have virtual IPs for each member. Just it's not possible now. We'll come back to it. We definitely know it's a problem. So to go back to the demo, let's hope that everything came up. Oh my gosh, I got lucky. So I've got my 3 members running. As you can see, they all have the same names that I was talking about in the demo. On the overview page, I can see I have 3 pods, and they're listening on 2 ports. So there's nothing really, as far as Kubernetes and OpenShift is concerned, the pods are basically all the same. All we saw was that they were part of the same stateful set, and so we group them together in the UI. The service didn't change all that much, so let me drop onto the command line. So I'm going to run the demo, and we'll see if this works. So let's hope. So this is kind of Prashanth's simple hello world for ZooKeeper. So what this does is it connects using exec into one of the members of the ZooKeeper cluster. So in this case, I think he connected to Zoo0. And what he did was he just made a simple create call that went and created a single key in the ZooKeeper cluster. And then we connect to the second instance. And I don't know that it actually prints the name out down here. Let's see if I can find it. Yeah, so we exec into the, I'll show you the test script so you guys can see. So the test script just execs into we just exec into the first and the last containers, and we run a command line from ZooKeeper, and we were able to read our key. If I shell into, if I go into the container, run bash because I want type ahead. So just like any other Kubernetes cluster, I can exec into things. I can run on the cluster. If I run an ls from within this member, I see the instance. So there's a lot going on that's hidden inside the setup logic here. I think the first thing that I would say is when we talk about stateful sets, the idea is to put enough primitives in place that this is easy to do, and possible to do safely. But it's not magic, right? There's no magic here. This is saying we have a basic idea. We want to create multiple copies of something. Kubernetes is going to go handle all the life cycle of these. If a machine goes down, Kubernetes is going to take care of it. It'll bring back a new one if it can. All the existing Kubernetes primitives work. But ZooKeeper, we had to do a little bit of glue code to set that ZooKeeper cluster up. And that glue code is actually a really important part because each of those clustered bits of software I showed, those aren't simple systems, right? If you ever run an Elasticsearch cluster or Kafka or ZooKeeper or etcd or MySQL master slave sharded cluster or Hadoop or HDFS, there's lots of things that can go wrong. I think I never want to leave people with the impression that stateful sets are going to just magically make problems go away, but they're trying to provide a rock-solid primitive that people can build higher-level logic on. If you have 10 Elasticsearch clusters, you may still need to do some actions administratively to keep those clusters up to date and do rolling updates and to handle those tools. And over time, the goal is to get the community to be able to help pull together examples and tools that work. But I suspect that for the next couple of years, when you look at these things, you're going to still have systems that have really good fundamentals. You can depend on Kubernetes to keep things running, and you'll build tools on top, scripts, systems, patterns that make this easier, or that make it easier to reason about what's going on. It's not going to magically solve all problems. And so I would caution that if you're looking at stateful sets today, if you're trying to use stateful sets, if you're coming and getting involved in Kubernetes, you've heard about these amazing things that can do all of these wonderful things for you, take a deep breath, step back. You guys know the systems that you run and you work with them. We're going to get better and better and better at these pieces. But for now, they're still alpha. And one of the reasons they're still alpha in Kubernetes 1.3 and 1.4 is there's a really big problem. So I talked before about a replica set that uses a persistent volume from AWS. If I start up 3 of those, then, sorry guys. If I start up 3 of those, only one of them is going to come up. Kubernetes will come along. If that node goes down, the cloud provider and all this magic will actually work to detach that volume from the node, and then it'll start up a new pod, so you can get availability that way. There's a trick. And so today in Kubernetes, if a node goes down, if it stops responding, stops checking in, we evacuate it. And after it's been evacuated, and if it hasn't responded for a long period of time, we say, you know what, we don't need those pods anymore. And so we go delete each and every one of them. That doesn't mean that that pod stopped. So the beauty of distributed systems is the masters have no idea what's happening on those remote systems unless they can talk. And if they can't talk, it doesn't mean that the world is proceeding normally. It means crazy, insane things are happening on the background, and buyer beware. And this is something that sysadmins for the last 50 years have dealt with, and we've built more powerful tools to deal with this, things like Pacemaker, virtual IPs, Keep Alive D. We've built systems that work together to detect failures and to help administrators reason about them. So if the pod hasn't been stopped, because for whatever reason that node can't talk to the master, but it can still talk to the other ZooKeeper members, if we created a new pod at that point, we would go and actually have 2 pods running at the same time because we force deleted it. We said zoo0, gone, deleted. Oh, look, there's no zoo0 anymore. I'll go create another one. So starting in 1.5, we fixed this. And this is all my fault, by the way. So when I put in Graceful Deletion to Kubernetes, I take full responsibility. We were a little aggressive about going and cleaning stuff up. I was brought to sanity by the excellent community members, including some people in this room who I won't call out by name. In starting in Kubernetes 1.5, and this is really important, when the system detects a node is down, it'll record that the node is down, and it'll actually say, I want to delete the pod. But because we have Graceful Deletion in Kubernetes, Graceful Deletion says, I want to start deleting the pod within a maximum window, and when it's done, the node says, OK, it's done. I go delete the pod from etcd, or from the API server, which is basically the same thing. In 1.5, when this happens, we'll evacuate, but we won't go and force delete stuff. So it'll still be there in the API. You'll still see zoo0. It'll say it's unreachable. As an admin, you have a choice. You can say, I know that the node this pod was on is gone. If you're running on a cloud provider like GCE or AWS, this is going to get magically solved for you through the beauty of cloud internet systems, except when it doesn't work and your data all gets lost. Don't sue me. As an admin, you'll have the choice to break the deadlock. If you're an admin and you know that node is gone, you can go force delete the pod, and the stateful set will pick up the next piece and take over. It'll go create a new pod. But otherwise, it'll fail safe, fail in the direction of causing the least possible damage, and you'll run at a reduced availability. So if you have 3 members, one goes down, you'll have 2, that's enough for ZooKeeper to keep running, but your failure margin will have been degraded. And obviously, if you're running Kubernetes today and you don't have an alerting system that tells you when nodes go down, you should add an alerting system that tells you when nodes go down. The cluster is not perfect. The real world is a crazy, ugly place, and bad things happen. So monitoring, understanding how the system is working is critically important, and this is a part that we're putting in just to make sure that there's a base level of logic that people can reason about to be as safe as possible. Future work includes, I talked about keep alive D and concepts like shoot the other node in the head, which sounds really traumatic, and we probably won't call it that when it goes into Kubernetes, because that might also be somewhat contentious. No shooting in Kubernetes. The idea is more broadly called fencing. Node goes down, you say, I can't necessarily guarantee that I'm going to be able to shut that node down cleanly, but the rest of the cluster can act to limit the impact that node might have on the rest of the cluster. So this is really common in the storage space. Used to be storage systems didn't have very good controls over who can talk to the storage system. So if you have an iSCSI or fiber channel device, anybody on the network can go talk to that endpoint. And if we created another pod and two people thought they were the same one, write the same data, bad things happen. Fencing is usually the pattern of in software or in hardware or at the networking layer or at any of 1,000 systems saying, block this device from talking to anyone else, or don't accept requests from this node that went down, or talk to the IPMI hardware on the rack and physically shut it down. And maybe there's people out there who have like a 100-pound iron weight that drops on the machine or something. That'd be pretty cool. I'd like to see that. But in the future, we want to make it possible for people to build fencing on top of Kubernetes, so that there's an independent agent that could be customizable. It could be your admin tools. It could be something that ships as part of the box at Kubernetes for bare metal systems that can come in and say, I've got failure detectors. When I see something go wrong, I can help Kubernetes resolve this partition. And the fencer might be someone who, if they're absolutely sure that machine's gone, they can take automated action. So this is a lot of future work here. The goal is to build a sane, reasonable system that people can layer on top of. Stateful sets will enter beta in 1.5. It's really important to us that you be able to reason and trust that the stateful set is not going to lose data, which is why 1.5, with the change that I talked about, is going to be when it goes into beta. We'll probably have a fairly long beta. We want to get feedback, examples, features that are missing. We need the ability to update stateful sets. I'm sorry to take away more of the pretty pink bow around stateful sets. The initial version in beta won't allow you to update them, but you can script updates to do it. And partially that's because of crazy systems like, I hope nobody hears from Elasticsearch, like Elasticsearch, where you actually need, because Elasticsearch has sharding, and there's internal concepts that Elasticsearch needs to know that you're taking nodes down and react appropriately. If you shut down a bunch of nodes in random order, or a bunch of pods in random order, and all that data gets lumped onto one box, and people are still slamming data at that system, your whole cluster may come over. So it's not a trivial problem. We want to make more extensive tools for operating sets. If you guys saw the announcement from CoreOS last week, they open sourced 2 tools that build on some of the ideas that have been discussed in the stateful set design. The idea of an operator, which is basically just an automated process that makes it easy to stand up etcd clusters or a Prometheus cluster, and handles that sort of resolution of what happens. So etcd has its own particular foibles about how it's initialized and how you add and remove new members. And the idea of the operator is you formalize some of that knowledge into code. But one of the challenges is, well, does that generally apply to Elasticsearch? No. And so one of the things we want to work with in the community is finding the points of commonality above this base layer for things like operators and scripts and tooling and hooks that we might add back into stateful sets over time. And we want to add tests and documentation. Obviously, if it's not easy to go try this out and understand how it works, it's not much good to people. Local persistent storage. So I talked about persistent volumes if you have dynamic provisioning. But if you're running on bare metal and you don't have this massive cluster of auto-provisioning stuff, local persistent storage is one way, not the only way, of making it a little bit easier to do. I create 3 members. Instead of having to go and provision a Ceph block device for that, I would like to be able to create a local volume that's attached to that machine. And I have to understand the trade-offs there, right? That data is located on that machine. Somebody eventually would have to go make it move. You'd have to deal with downtime. We're not quite there yet, but it's something that's on the roadmap for Kube that enough people need local persistent storage that it's going to be really important to do. You can emulate this a lot of ways today, but we want to make it easier out of the box. And as the astute gentleman noticed, software that needs stable IDs or stable IPs for each member. So Cassandra has a particularly nasty habit of taking those nice generic DNS addresses we give it and then turning that into an IP address and sticking it in a database. So some of the work that we talked about, it is possible to build a script on top of that watches the Cassandra cluster and goes and updates the Cassandra member set. We want to explore solutions with the community, but probably in the short term, we have no good answer for this. I'm sorry. It's all my fault. We might, in the future, look at solutions like VIPs, but VIPs are hard. Yep, question?
Yeah, I saw the years worth of dashing on was template expansion, and I didn't see you mention that in your example.
There is no template expansion. And so, the question was, there's no template expansion in that template. Template expansion is really, 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 really hard. Probably there's Googlers in the room that can talk your ear off about all the foibles, about the ways that config management systems fit together and the different trade-offs they make. We, in favor of starting down that path, we said, well, let's take a step back. What are the two things that we can provide out of the box? IP, or stable identity and state. It's still possible to use any config system you want to go generate it. Helm charts should support this today, because Helm charts just deal with API objects. And so what we'd like to do is, as that discussion evolves, kind of keep it orthogonal. Nothing in stateful sets depends on template expansion, because we try to provide that base primitive. And there's actually no guarantee that a stateful set is just a single stateful set. So if you have masters and workers, you could end up with two stateful sets. And so we know that people are going to want to compose these rather than stitch them together. So, question back there?
Is anti-identity on the roadmap for stateful sets?
So everything that works on a pod today, including node interaffinity, should work today. So all you have to do is set the beta annotation for intra-pod affinity, and it'll spread them automatically. In fact, because every stateful set basically requires a service, if you have that scheduling predicate set, which it is by default, I still think, yes, thank you, Tim, that's set by default, all members will land on another node unless there's only one node. So I'm running on my laptop here in the demo. It's running in a VM. There was no option, so it put them all. If you had a hard affinity rule, it would have stopped at zoo 0 and then started spewing errors. Other questions? Sir?
I think I read on the Kubernetes page the startup sequence. Is that supported where, like, I'm looking at older traditional application containers, they need to be started up in a very specific way, and then, what if one of those containers fall down and start them all again?
Yeah, so, and I didn't quite show it, but the stateful set always goes from lowest index to highest index. If you deleted 0, it would try to go and recreate 0. There's still a lot of wrinkles here. The documentation that I alluded to, we want to make it easier to describe exactly what you can rely on and show examples. I would say today the ordering might be enough, but it's easy to back yourself. Again, like the hard part about all this is it's distributed systems, which we can't magically solve. So what we try to do in the stateful set is we try more than anything else to be consistent first. We will never actively introduce inconsistency. And so working through how you would apply that inside, for instance, in ZooKeeper, we will never create more than 3, and we will never create 2 before the first one, or never create 0 indexing. I really wish we hadn't done 0 indexing. That's just my personal beef, but I was overridden on that. The third one will never be created before the first one. And so when you do initial bootstrapping, if you've seen it come up at least once, you can make some reasoned decisions about it. It's still a little tricky. Sir?
Is the replica count or the cardinality part of the model exposed to the download API? And if your identity be I'm 0 out of 3?
So no. And part of the reason for that is you can actually, and there's actually an active PR discussion on this. If you put the cardinality as a downward API, and then you change that cardinality, and then if you can't reason about, so an example here is I start with 3 ZooKeeper nodes, and then I scale up to 4. And I scale up to 7, I add 4 more. If you hard-coded 3 in your initial template, just as an environment variable or whatever, then you could have formed an initial core and we would have never created more. if you hard-coded, if that changed, we would have to go delete 0, 1, and 2 and ensure that they observe it. Otherwise, when we create those 4, so the scenario would be the first 3 get partitioned before we detect it, and those new 4 come up. That's actually a majority. And if they're not carefully written to deal with the fact that there may be another majority in the cluster when you resize them, you could end up breaking it. And this is the general challenge is many of these systems have innate tools for handling membership change that require a certain set of guarantees. There has to be a majority at all time to add new members. And so one of the things that we're trying to be very cautious about is allowing people to accidentally introduce initialization splits. And the documentation, there's a lot of this is in people's heads or in PRs or discussions. We actually want to have a really good document that says, here's how you can safely reason about it and the guarantees we provide. It would be easy to add that in the template, but as you change the cluster membership, if you didn't treat your own internal consensus, it's possible to get split brain. Sir?
So if I step back here, I think possibly there's kind of a fundamental dilemma, like dealing with this container technology, like, okay, stateful versus stateless. If you focus on stateless, probably easier problem domain, like, okay, easy to do, whatever stuff, but once you start to bring up stateful app, this framework itself, and then as you found already, okay, it's not easy, it's a very hard problem domain. And I don't know if they're using right objection, this is like a kind of next open source version of Borg that Google probably, and I don't know, Borg initially didn't have this stateful app capability at all, and there was a reason to do that for them, or?
So I can't speak to Borg, although I could call Tim out if he wants to talk about that. He's hiding. So the answer is that, in general, and I think I can speak for everybody in the Kubernetes project, is distributed systems are hard. They're not going away. And rather than hide from that, what we want to build is a system that can eventually deal with both stateless and stateful applications correctly, safely, and work with the communities to build it. There's no other path forward, right? Because everyone who needs a stateful database today can guarantee you they've got hacked up versions. No offense to anybody out here who has hacked up versions of anything. We're using software that does all these things today. These aren't new problems. As much as possible, trying to bring communities of expertise together so that we're all solving some of the same problems and everyone can benefit is, I think, what Kubernetes can bring to this. It's worth trying because there's no going back. And if you're reasoning, every single person out there who cobbles together a script that sets up a ZooKeeper cluster on AWS or on GCE or runs it across a set of Docker containers, those are really hard problems. Somewhere, somehow, we have to sit down and make sure that those can be built on good foundations. And I think they're solvable problems. It's going to take a while. Like, it's not an easy problem, but I think it's worth solving. Sir?
Is there an expectation of the local storage to be actually incorporated into the scheduler?
There's been the proposal is basically, yes, that you'd create a persistent volume claim. The scheduler would put you on a machine that had enough storage to satisfy your request, and then some process would go and record that so that we could say, no, you are not allowed to run on a different machine for this persistent volume. There's a couple of proposals out there. Tim nodded his head at that. I think we'd like to do this over the next couple releases. There's a lot of bandwidth problems in trying to get this, because it's a hard problem. We don't want to screw this one up either. So it is every single person I know who has run Kubernetes has asked for this. It's something we will do. One more?
Do you think the initialization pods are a good place for passwords where you want to start up an application, give it a password, but then you don't want the password to live on the pod after it's started?
I think that is an option. So the question was, are initialization containers a good place to do secret download? I think the answer is a cautious yes. The problem is that for initialization containers to communicate with app containers, you have to write to disk in the first place. So there's maybe like a small challenge there. I would say that one of the scenarios that we have talked about quite a lot is integrations with things like Vault and other distributed secret systems where the responsibility for getting the secrets into the container is clearly delineated from the application itself, but we would need to be very careful about how that's implemented. Sir?
I might have missed this, but am I right in guessing that you're basically using DNS for identity protection?
DNS is provided by Kubernetes. Identity protection is provided by the cluster. and then the DNS reflects what's on the cluster. Today, that is a strongly consistent feedback loop with a couple of small wrinkles. Our goal would be to ensure that it is impossible for DNS to be not something you can't reason about. But knowing the problems of DNS, you could also look at the endpoints array that backs DNS and fetch that data. Because that's stored in etcd today, that can be strongly consistent. But we want to, there's a caveat here, which is the answer should be absolutely yes. And we need to make sure the systems and safeguards are in place so that it doesn't become no.
So you basically have to somehow deal with time to live at DNS. Might have like old information or something like that.
That's true. And one of the ideas here would be that bootstrapping of these clusters is usually the first part, and then the members try to connect to the masters anyway. When the members try to connect to the masters, if you've built a system that's consistent and you try to talk to something that's been split-brained, either you cause the split brain by violating the cluster safety guarantees, or you're unable to join that cluster. So we want to be able to work through how people can write the system so that it is safe. But yes, there are a lot of small things that are very important to call out and help people work through. Right? I know that we're over time. Are there any other questions? You can please come up here and ask if afterwards. Thanks, guys.